Swayam Prabha. Digital India. Educated India.
Welcome to the course Analysis of Variance and Design of Experiments. So you can recall that in the last lecture we started a discussion of 2 to the power of n factorial experiments, and we had considered some basic definition concepts, and then we took a very simple example in the setup of 2 square factorial experiment. And based on that we had only 4 observations. And based on that, we had tried our best to understand that how the main effects and the interaction effects of those 2 factors can be obtained. So if you try to see, we have now here 2 factors A and B. In the example, they were irrigation and nitrogen, but now I can talk in general terminology because now we have understood that how are we going to represent these factors and their different levels. So now the question is very simple. You have here 2 factors. Each of the factor is at 2 levels. So there are 2 factors A and B. They are at 2 levels, A0, A1 and B0, B1. Now we have to utilize the observations on these 4 treatment combinations in such a way so that we can estimate here 4 possible effects. One is the main effect due to the factor A, main effect due to the factor B, and the interaction effect due to factor A and B. Beside these 3, there will be one more, which is the general mean effect. Well, this setup which I have explained you here, I am assuming that there is only one replication. Well, because you can replicate this setup. So once you are trying to replicate it, the same concepts have to be extended further. The way you have thought that how can you measure the main effect, the way you have thought how you can measure the interaction effect, general mean effect, etc. So this is how we are going to find all these effects, and based on that we have to understand that how are we going to conduct the analysis of variance. So we are going to consider here the setup of randomized block design, where we are going to implement the concept of 2 square factorial experiment, and we will try to understand that how the things are moving further. My promise to you is that once you understand that how the things are moving further, after that you have 2q factorial experiment, 2 to the power of 4 factorial experiment, or any type of factorial experiment, it won't be difficult for you to extend this concept and to understand how to conduct the analysis of variance using the concept of factorial experiment in any type of design. So let us begin our lecture and try to understand how the things are moving. Okay, so now we are going to consider here the 2 square factorial experiment, and our primary objective in this lecture is that we want to conduct here the analysis of variance. Right. So as I told you in the last lecture also, that if the number of levels for each factor is the same, we call it as a symmetrical factorial experiment. And in case if the number of levels of each factor is not the same, then we call it as asymmetrical or mixed factorial experiment. And we are in this course, we are going to consider only the symmetrical factorial experiment. Well, the extending this concept to a symmetrical factorial experiment is not difficult, right? The only thing is this: given the time frame, given the course structure, I will be discussing only the symmetrical factorial experiment. So now we have now understood that through the factorial experiments we can study the individual effect of each factor as well as the interaction effect, right? Up to now you have considered only the 2 square factorial experiment, so you have only here two main effects A, B, and one interaction effect AB. But if you are going for higher order factorial experiments like as 2 cube factorial experiment, then you are going to have the main effects A, B, and C, the interaction effect containing 2 letters, that is AB, BC, and AC, and the interaction effect containing all the factors, that is ABC. So you will see that how are we going to compute them using the observation from different treatment combinations. So as I said earlier, I will repeat again that an important point to remember is that the factorial experiments are conducted in the design of experiment setup. For example, the factorial experiment is conducted inside the setup of a randomized plot design. So that is what we are going to now consider in this lecture. So once again, a quick review about the symbols and notation. So now we are not going to talk about this I0, N0, I1, N1 as the irrigation or nitrogen factors, but we are simply going to develop everything in terms of the factors A, B, C, A0, A1, B0, B1, C0, C1, and so on. Whatever I am going to explain you here, these things can be extended very easily for higher order factorial experiments. So from that point of view, you have to understand these things. So as we have discussed earlier also, the general notation for representing the factors is to use the capital letters, that is the uppercase alphabets, capital A, capital B, capital C, etc. And the labels of the factor are represented in lowercase alphabets, that is small letters in our common language, what we say. So if there are 2 levels of a factor A, then they are indicated by A0, A1. Similarly, if the factor B has 2 levels, then they are indicated by B0 and B1. And alternative represent is that this A0 and A1 can be represented by here 0 and 1 also. And similarly, the factors of B are then becomes here, say 0 for B0 and 1 for B1, right? And one thing I would like to make it clear before we go further, that you will see that when we are trying to develop a sort of analogy to understand or to find different types of main effect, interaction effect, and while we are trying to deal with the different type of treatment combination, we understand what is the meaning of here AB. That means you are trying to give the treatment combination, say A of factor A and B of factor B. That means A and B both are at level 1, and then you are trying to obtain its response like as YAB. So at many times we will be writing here directly here as say AB, and just to explain you, just to understand it, just to simplify the expression, sometime we will be considering this AB as if this is an algebraical term like as A into B or A multiplied by B. It is not correct because I am not considering this thing. But just for the sake of simplicity in understanding, this will be our understanding that in order to simplify many complicated expressions, sometime he will try to use this sort of trick, you can say, for the sake of convenience. But this is our understanding, that we agree that we understand the meaning of A, this B, and this AB. They are different, but still we will try to do it. And you will see that this will make our lives very simple and this factorial experiment very easy to understand. So now we are going to represent or find or explore how this main effects and interaction effects including the general mean effect, can be expressed using 1, A, B, and AB. So now, if you try to recall, in the last lecture we had considered a very simple example based on the two levels of irrigation and two levels of nitrogen. We had found the main effect of nitrogen, main effect of irrigation, the interaction effect of irrigation and nitrogen, as well as their general mean effect. Right, and based on that, parallelly, we had expressed all those treatment combinations in terms of 1A, B, and AB. And we had expressed the main effects of irrigation and nitrogen as a main effects of A and main effects of B, and the interaction effect between irrigation and nitrogen, that means different levels of irrigation and different levels of nitrogen. We had obtained the interaction effect also, and we had also expressed that interaction effect in terms of factor A and factor B, or we have used that expression using the treatment combination 1 small a, small b, and small ab. Now, what I am doing here, I am simply trying to write down those expressions from that example here. And you can verify it that the main effect of A that we had found, this was here like this: A plus AB by 2 minus 1 plus B divided by 2. And similarly, the main effect of B was found here like this: B plus AB minus 1 plus A divided by 2. And the interaction effect between A and B was found as here AB minus B divided by 2 minus A minus 1 divided by 2. And the general mean effect was found here as a 1 plus A plus B plus AB divided by 4. So now, you have to understand here that there are two types of things. One, the quantity in the numerator, and other is the quantity in the denominator. When we are trying to consider here the main effect of A, B and interaction effect of AB, then we have the denominator here only 2. You can see here. But when we are trying to consider here the general mean effect, then we have the denominator here as say 4. Right. Now, in case if you try to simplify it here, the main effect of A can be written here as like this: 1 upon 2 will come outside common, and then whatever is there here, AB minus B plus A minus 1. Right, you see, when I'm trying to say, you have to be careful with my pronunciation, that when I said AB here, I'm trying to say that this AB inside the parenthesis, but it is difficult for me to say again and again. Right, so that is our understanding. You are trying to look in the slides, and then I'm trying to explain you, right? So now, and similarly, if you try to take here this thing here in the main effect of here B, you can take out this 1 by 2 common, and you can write down here AB minus A plus B minus 1. Their interaction effect of A and B, this is here like this. Right, I'm simply trying to take this 2 common, and then AB minus A plus 1 minus B comes over here, and similarly here for the general mean effect, I try to take this 4 outside, and then I have here 1 plus A plus B plus AB. Now you see what I'm going to do here. I simply try to consider for a while, try to look at the main effect of A. I try to write down this AB here as say A into B. As I explained you earlier, this is mathematically incorrect. This is not correct. But just for the sake of simplicity in the representation of these effects, which is going to help us a lot when we are trying to find out the higher order effects in this higher order factorial experiments. So for a while we are considering it. So now this becomes here minus here B plus here A minus here 1. Now can you treat it just for a while as a mathematical expression? You can see here this becomes here, you try to take here common, this here b, and this becomes here a minus here 1, and plus this is here a minus here 1. And if you try to take it here, the common a minus 1 into b plus 1. Or you can write it here more simply as here a minus 1 and b plus 1. So this is what I am writing here, that a minus 1 into b plus 1 divided by 2, and I have explained here that how we have obtained this expression. Right. Similarly, you can obtain here the main effect of b here as a plus 1 into b minus 1 divided by 2. The interaction effect between a and b as a minus 1 into b minus 1 divided by 2, and general mean effect here as a plus 1 into b plus 1 divided by 4. Now, at this moment, I request you to use some your common sense and try to see the structure. Try to compare these 4 expressions which I have highlighted in orange color, and try to see how I am going to proceed further. You can see here in these 4 terms, this a, there are 2 factors which are related to a and b, and which are combined with the number 1, but the number 1 is appearing at some place with minus sign and at some place with plus sign. Try to observe this phenomena. So if you try to see here in the main effect of a here, this a is appearing here with the minus 1 sign and b is appearing with the plus 1 sign. When I am trying to consider here the main effect of b, then a is appearing with plus 1 sign and b is appearing with minus 1 sign. So if you try to compare these 2 observations, can you see here that the sign of 1, whether it has to be minus or plus, depends upon the common alphabet between the treatment effect and main effect? What does this mean? If you try to see here, this is here capital A, and now you are using here a small a. So a is a for me. So when this letter is common, then we are using here minus sign, and if this letter is not common, then we are using here plus sign. Very simple logic. It may not be mathematically correct, that I agree. But once you write this thing, you can come back and you can express the same thing in this format also, which has no problem. Right. Now, if you try to do the same thing in the main effect of b, now here is here b and here is here b. For me, small b and capital B both are b. So when this letter is common, then this one is appearing here with minus sign, and I am writing here b minus 1. And for the alphabet which is not common, that is here a, there that I am writing here as a plus 1. Now, in case if you try to implement the same logic in writing the interaction effect of a and b, you can see here that there is a factor here capital A, so I am using here a minus 1. There is here a factor b, so I am using here a b minus 1. And in the case of general mean effect, there is no capital A, no capital B, so I am using here both a and b with plus sign, and I am writing here a plus 1 and b plus 1. Right. But this is only a way out. That I am simply trying to show you here that in case if you try to see those things, then this is not looking mathematically correct. Means I am simply trying to use a wrong mathematical logic to explain you these things. But there is no problem. You are simply trying to understand how you can write down the main effect, interaction effect without much efforts. So I am just doing here a symbolic calculation. I am not using here any mathematical calculations when I am trying to write down AB as A into B. This is only a symbolic calculation flavored with some mathematical logic, you can say. But once you can write the main effect of A as A minus 1 into B plus 1 divided by 2, then after that you can simply just simplify it and then try to write down the entire expression. That is the correct expression. So now I have given you here the first idea, that how are we going to write down all such expression for any general order factorial experiments. Now, in this example, I have used here two types of denominators, 2 and 4. But since I had explained you the example of irrigation and nitrogen, so from there I can explain you that how these 2 and 4 are coming here. Because we were trying to consider different types of combination using their arithmetic mean, etc. But they have a proper logic. All these things, whatever I have told you, that sometimes you have to take A minus 1, sometimes you have to take B minus 1, sometimes A plus 1, sometimes B plus 1, they are not coming arbitrarily. They are based on pure mathematical things. And they are based on the concepts what we have studied in linear estimation. But the only thing is this, now we have to see that how these things are happening. So the fact is this, these things were not developed like this. They were developed using the statistical theory and estimation theory. But after that, in order to explain it in a simple way so that people can understand, students can understand, possibly this way was adopted. So this is what you have to keep in mind whenever you are trying to find out such effects using these types of quote unquote tricks. Right? Okay, so let us begin here further. So now you can see here the roles of this plus and minus sign as well as the divisor. There are two effects related to capital A and capital B, that's factor A and factor B. And to obtain the effect of a factor, write the corresponding factor with minus sign and others with positive sign. For example, when we are trying to write down the main effect of A occurs with here a minus sign, as you can see here, there's A minus 1, and B occurs with here the plus sign, that is here B plus 1. And in the case of interaction effect AB, both the effects are present. So A and B both occur with plus sign, as say here A plus 1 and B plus 1. Right? And one thing you have to note down, that we have used only here 4 values, 1, A, B and AB, and these values are combined together with the signs plus minus. Somewhere it is plus, somewhere it is minus, and then they are found using a special type of, a typical type of differences of these averages. Right. So we note that the main and interaction effects are obtained by considering the typical differences of averages. So they have the divisor 2, whereas the general mean effect is based on the treatment combinations, and so it has a divisor 4. Right, that is not arbitrary, that is based on certain logic, and later on I will try to show you that how this is related to the mathematical concepts of linear estimation. Right, so this is a well defined theory, and all these results, they are based on well established statistical theory and logic, and this logic helps in writing the final treatment combination easily. That is the only thing. And Means I have done this, but I will try to demonstrate it with the proper reasoning also. Right, now if you try to see whatever you have obtained here, you can see here in these cases, you can see here, these are here, see here, some plus minus sign here, you can see here. Right, you can see here, these are some signs. So now I try to combine these things in a very simple fashion. I try to write down here the effects or the factorial effect, like is here A, B, AB, and the general mean effect, say M. M means mean. And then we have here 4 treatment combinations, 1, A, B, and AB. And now I try to write down their corresponding plus and minus sign in this table. So corresponding to here M, we have a all plus sign, 1 plus A plus B plus AB. So I can write down here as a M, here as a 1 plus A plus B and plus AB. And then I am writing here this divisor 4, so I can divide it by here 4, and this is going to give me the value of general mean effect M. Now, whatever the plus and minuses are appearing in the main effect of A, I try to write them here properly, like this here, minus plus minus plus. This means here what? This 1 is appearing with here minus sign, A is appearing with plus sign, B is appearing with minus sign, and AB is appearing with plus sign. This means if I want to rewrite this expression looking at this table, I can write down here minus times here 1, which is coming from here, then plus here A, which is coming from here, minus times here B, which is coming from here, and plus here AB, which is coming from here. And then the divisor here is 2. So I try to write down here like this 2. Now you can verify here. This is the same expression you had found, A minus 1 plus AB minus B. So you can see here in this table, you are getting here A minus 1 plus AB minus B. Right, and similarly you can do the same exercise with B and AB, try to find it out. So this is another way by which we try to represent all these effects in a very simple way, which are very easy to understand. Now, the next question comes. You have obtained all these effects, interaction effect, mean effect, etc. But then, what is the model corresponding to this design? Because now we are going to consider this factorial inside the design, so we believe that, or we assume rather, that they are conducted under the setup of randomized block design. That is the most simple way to understand it. So the model corresponding to the 2-square factorial experiment is now written as here yijk is equal to mu plus ai plus bj plus abij. That means this is the interaction effect, plus epsilon ijk. Now you understand, now you know all the meanings. Epsilon ijk is the random error component, then ai is the effects of factor A, bj is the effects of factor B, and this AB, when I am writing it like this is the effect of factor AB. And now here I have only here I equal to 1 to 2, because I have only here 2 factors, and j is also from here 1 to 2, that means there are only 2 levels, and then we are trying to observe a small n number of observation for each of the treatment combinations. So we are writing here k is equal to 1 to up to here n. So this is how we are going to write down the model, and you have to keep this thing in mind, because we are going to develop the analysis of variance model, and later on when we will try to understand the concept of confounding, I will be using this model. Right. So now you can recall that in this case I have taken only here 2 factors with 2 levels each. But as I discussed in the last lecture also, we can have different types of situations that we can have 2 factors, say for example irrigation and nitrogen, and they may have different levels. For example, irrigation may have 2 levels indicated by say I0, I1. The nitrogen may have 3 levels indicated by N0, N1, N2, etc. Right. So now if you try to see what will happen if you try to conduct this experiment in RBD and in factorial experiment. So when the experiments are conducted factor by factor, then much more resources are required in comparison to the factorial experiment. For example, in this case, what you have just considered for 2 levels of irrigation and 3 levels of nitrogen, if we want to compare their effects, and if we conduct the randomized block design for the 3 levels of nitrogen at N0, N1 and N2 levels, and 2 levels of irrigation at I0 and I1 level, then in case if we want to have 10 degrees of freedom for the error variance, then we need here 6 replications on nitrogen and 11 replications on irrigation. So the total number of plots to conduct such an experiment is going to be here 40. And then you can estimate the required cost also. Right. And for the factorial experiment with the 6 combination of 2 factors, because you have 3 levels of nitrogen, 2 levels of irrigation, so there are going to be altogether 3 into 2, 6 treatment combinations. So the total number of plots which are needed are only 18 to get the same precision. Right. Well, this comparison which I have shown you, I am assuming that we have only one replication of each of the treatment combination. That is what you have to keep in mind. But my idea was simply to give you an idea that what is the advantage of factorial experiment and how the things are going to change. And whatever expressions what I have given you for this A, B, and M, they are based on the assumption that we have only one observation per cell. But if you try to replicate them, and if there are replicated observations for each of the treatment combinations, then the expression for the main and interaction effect can be modified. What are we going to do here? I am simply going to take here R in the denominator, and now you can understand why this is coming. Means earlier you had obtained the main effect of A by taking the average of some treatment combinations. Now you are going to repeat those treatment combinations, say R times. So the total number of the observation on which you are going to take the average will become 2R. And the same story will continue with here B, AB and M also. Now this general mean effect is the arithmetic mean of all the observation from all the treatment combinations. So now you are trying to repeat 4 treatment combination R times each. So you are going to have here 4R number of observations. So the total number of observations in this experiment will be 4 into R. That is why you have written this A, B, AB and M properly. But surely we will try to look at this in a more scientific way using the concept of linear estimation. Right, and now we try to do it. We try to understand what is the statistical theory and concept related to these expressions. And I am promising you, you know each and everything. Right, so now if you try to see, you are trying to obtain here the observation. For example, when you are giving the treatment combination 1, you are trying to obtain here an observation like this, Y subscript 1. Right. Similarly, if you are trying to use here the treatment combination here A, you are trying to obtain here an observation like as here YA. And similarly, if you are trying to obtain the observation on Y, this is here the observation YB. And when I'm trying to use the treatment combination AB, then we have here the observation Y AB. Right. Now, the same thing I try to express simply here as uh, see here some vector here y say star like this one, right? But now, just for the sake of simplicity in expression, I'm trying to write down this y value being indicated only by their subscript 1 A, B, A, B, like here this. So, but that is our understanding that these are the y values corresponding to the treatment combination 1 A, B and A, B. Right. Now, if you try to look at this expression, what you have just written. So, this will become here something like 1 over 2R y A B plus y here A minus y here B and minus y here 1. Right. So, this I am trying to write down here like this. Right. But if you try to see here, if you try to write down this combination here, and if you try to write down here this vector here y1, ya, yb, and here yab like this, then you need here what here? What is the sign of here y1? This is here minus. I'm writing here minus 1. What is the sign here ya, which is here plus 1? I'm writing here plus 1. And what is the sign here of yb, which is here minus 1? So, I'm writing here minus 1. And then what is the sign of yab? This is here plus 1. So, I'm writing here a vector of order 1 by 4 and a vector and that is containing only the elements like 1 minus 1 and another vector here of order 4 by 1 which is containing all the y values. So, now and then yeah, obviously 1 upon 2r will come over here. So, now if I try to write down here, this is a sort of vector here L which is related to the main effect A. So, I can write down here that LA is my vector here like as minus 1 plus 1 minus 1 plus 1. So, I can write down this expression as a LA transpose and this vector here I am trying to write down here as a y star. So, I can write down here y star and then this term will come over here like this. And the same exercise I can do with here B, AB and here M. Right. So, this is what I am writing here. So, now A is being expressed here as a 1 upon 2R LA prime y star 1 upon 2R minus 1 1 minus 1 1 and here this is here is y star. And similarly, you can express here B and AB here as a 1 upon 2R LB transpose y star and 1 upon 2R LAB transpose y star. So, this LB transpose is going to be here minus 1 1 1 and LAB transpose is going to be 1 minus 1 minus 1 1. Right. And then this y star will remain the same for all. So, now you can see here this vectors LA, LB, LAB, they are simply having two types of values, plus 1 and minus 1. But the way they are going to be arranged, that is different when you are trying to take the main effect of A, B or AB. Well, in case if you try to write down for here M, this is simply going to be here plus 1, plus 1, plus 1 and plus 1 only. Right. So, that is straightforward. So, now if you try to see all the elements inside this LA and LB are consisting of plus 1 and minus 1 values, and if I try to have your attention here, try to count the number of plus signs and number of minus signs, they are equal in all the cases. What does this mean? If I try to take it here in a very simple way, if you try to observe here, if you try to look at here, can I write down here as say like this here, AB minus B and plus A minus 1? Can you see here what is happening? Can you see here that this quantity is an elementary contrast and this quantity is also an elementary contrast, right? And if you try to look at this entire quantity, whether this is inside here A or inside here B or AB or say M, what is the difference between AB and M? M is different because it has all the 4 positive signs. But in AB and AB, we have 2 positive and 2 negative signs. And if you try to see all the values which are written inside the bracket for 1 AB, AB, don't you think that they are trying to create the contrast? Because they are linear parametric function. So now you can see here that whatever you have expressed here, A, B or here AB, they are all the linear contrast. And now if you try to recall, a linear parametric function is estimable only when it is in the form of linear contrast. That is the result which you have used many times and which you have proved when we were trying to develop the analysis of variance in case of one-way analysis of variance in the beginning of the lecture. And at that time you also learned the concept of orthogonal linear contrast. So you can see here this AB and AB, they are also the linear orthogonal contrast in the total response values 1, AB, AB, except for the factor of this here 1 upon 2r. 1 upon 2r is coming because of other reasons, because you are trying to take the averages, right? So I hope I have made it clear that the terms which you have obtained, all those expressions are in the form of a linear contrast. And now can you use the theory what you have learned in the case of linear estimation? In linear estimation, we have learned that if you have a linear parametric function, then how can you obtain the sum of its squares, and how can you obtain the distribution of the sum of its squares. So in case if you try to recall, we have studied that the sum of its squares of a linear parametric function L transpose y is given by this quantity L transpose y whole square divided by L transpose L. Now if you try to see what is here L transpose L, that is simply the total number of elements in the vector L. Why? Because you are trying to consider here only 2 types of elements which are here +1 and -1 in this case. And if there are replicates, and suppose if there are R replicates, then the sum of square is given by L transpose y whole square divided by R into L transpose L. Right, and about their distribution, you can recall that under the normality of y's, that you assume that yij or yijk, they are following a normal distribution with mean 0 and variance sigma square. This sum of square has a chi-square distribution with 1 degrees of freedom, and that is indicated by chi-square 1 like this. So now you see your problem is solved. Whatever you have done now, you have got a reason, a statistical reason, mathematical reason that why you are trying to do it. So now if you try to see, we can write down here the sum of squares for these factors A, B and AB without any problem. That is the most fundamental way to understand it. So you can write down here sum of squares due to here A, like as here L A transpose y star whole square divided by R into LA transpose LA, and which is simply your here 1 upon 4r, and then the same quantity over here, right? AB plus A minus B minus 1 whole square. And similarly, you can write down for here SSB and SSAB. Just try to consider the contrast corresponding to the main effect of B and interaction effect of AB, and then try to write down their squares and then divided by the, say, R into, say, the vector L transpose into the vector L, right? So now you can see here, this is, you have obtained the sum of square due to block as 1 upon 4r AB plus B minus A minus 1 whole square, and 1 upon 4r AB plus 1 minus A minus B whole square. And each of this SSA, SSB and SSB AB has a chi-square 1 distribution under the assumption of normality of this Y star. So now if you try to see, how are you going to compute the different components of the analysis of variance table in this case? So now you have obtained here the SSA, SSB and SSAB. So basically what you have done, you have computed the treatment sum of squares. How? That I will try to explain you. That is as simple as that. You are trying somehow to partition the sum of square due to treatment that you considered in the case of RBD into 3 different components, SSA, SSB and SSAB. So you can write down here SS treatment is equal to sum of square due to A, sum of square due to B and sum of square due to AB. Right, I will try to show you. Now, how are you going to find out the total sum of squares? This is the same way that summation I goes from 1 to 2, summation j goes from 1 to 2, summation k goes from 1 to r, y square ijk minus g square upon 4r. This is your here total sum of square, where g is the grand total of all the observations, summation over ijk on yijk. Right. So now you can see here you have obtained. Now, how are you going to find out the SSE? So the sum of squares due to error, this is obtained as we have discussed by subtraction, that is TSS minus SSA minus SSB minus SSAB, so that the Fisher-Cochran theorem holds true. And what about their degrees of freedom? The TSS has got a chi-square distribution with the degrees of freedom 2 square into r minus 1. Do you remember earlier it was n minus 1, and now n is becoming here, there are here 4 observations, so this is becoming here 2 square, and then you are trying to repeat it r times. So now n is becoming here something like 2 square r. So based on this, the SSE has got a chi-square distribution with the degrees of freedom, this 4r minus 1 from SSE and from SSA, from SSB and from SSAB, 1 degree of freedom each. So this comes out to be 4 into r minus 1 degrees of freedom. And now you have obtained all this sum of squares, so you can also obtain the mean squares due to A, B, AB and E just by considering the sum of square due to A divided by the degree of freedom 1. That will be for MSA, and similarly for MSB and SSB, they are going to be the same, and MSAB and SSAB, they are also going to be the same, and then MSC is going to be simply here SSA divided by 4 into r minus 1. That is the degrees of freedom which you have obtained here. Now, you have obtained the MSA, and one can very easily establish the independence of all these values without any problem. Then based on that, the SSA and SSE, they are going to be independently distributed. Both are having chi-square distribution, so I can take the ratio of these two variables divided by their respective degrees of freedom. Then that is going to follow a F distribution. And the same thing can be done for the factor B or AB. So based on that, now we can define here the F statistics for testing the null hypothesis about factor A, factor B, and factor AB as follows. For A, this is MSA upon MSE, which is indicated by here FA, which is going to follow F distribution with 1 and 4 into R minus 1 degrees of freedom under H naught. Then FB is going to be MSB upon MSE, which is going to have the same F distribution under H naught, that is F with 1 and 4 into R minus 1 degrees of freedom. And similarly here, the F statistics for AB will be MSAB upon MSE, which is indicated by here FAB, and that is going to follow here a F distribution with 1 and 4 R minus 1 degrees of freedom under H naught. Now, the decision rule. The decision rule is going to be the same for all as we have developed earlier. It is simply to reject the concerned null hypothesis when the value of the concerned F statistics, I'm indicating by here F effect. Effect can be effect A, B, or AB, is greater than the tabulated value of F, which is obtained from the table at alpha level of significance. And now, in case if you try to compile all these calculations in the form of the analysis of variance table, then we can express it here like this. So this is the analysis of variance table in case of 2-square factorial experiment. So we have here the sources as here factor A, factor B, factor AB, and here error. And their corresponding sum of squares are going to be here SSA, SSB, SSAB, and then we have total sum of squares, and then you can obtain here SSC. The corresponding degrees of freedom for each of the sum of squares due to A, B, and AB is 1. For total, this is 4R minus 1, and SAC degrees of freedom are 4 into R minus 1, which is obtained by subtraction. Then you can obtain here MSA, MSB, MSAB, and MSC, and then based on that, you can find out here the 3 F statistics, FA, FB, FAB, just by considering the respective MS and the corresponding MSC. So MSA upon MSC will give me here FA, MSB upon MSC will give me here FB, and MSAB upon MSC will give me here FAB. And after that, you can simply compute this F statistics, which are going to follow a central F distribution under H naught with the degrees of freedom here 1 and the degree of freedom of SSE 4 into R minus 1. You can obtain the tabulated values from the tables of F distribution and you can compare them. This way you can conduct the test of hypothesis for A, B as well as AB separately. Right. So now we come to an end to this lecture here, and you can see that in this lecture we have understood the basics of this 2-square factorial experiment, how different factors and interaction effects are being converted into a formal way using the statistical theory, rules, concepts, and finally how are you going to conduct the analysis of variance. Now, whatever we have learned that how you can very easily write down the main effects and interaction effect by writing them in the form of LA or creating that table of the signs plus and minuses, from where just by looking at the table you can write down all types of this interaction effects and main effects in terms of the treatment combinations. Now we are going to extend it further. Surely you can think that, okay, that means I have to write down all the treatment combination for higher orders and then we have to write down the table. It is not really correct. There are ways by which we have to write down only a few treatment combination in terms of plus and minuses, and then we can write the remaining part of the table very easily. So, but in order to understand that part, it is very important that you understand what we have done in this lecture. we have used some tricks, so-called quote-unquote tricks, and we have justified it with a strong statistical theory. And those tricks are not actually tricks; these are only the symbolic representation. Just for a while, you are trying to consider it, and then you are getting these expression very easily. So they are very helpful in real life experiment that without doing much algebra, you can write down the expressions and can find out the sum of squares and conduct the analysis of variance. So it is very important that before we go further, you understand each of this concept very clearly. So you try to practice it, revise it, and I will see you in the next lecture. Till then, goodbye.